Hey everyone, and thanks for coming. Most of our guests tonight will be online, as you might appreciate, because of probably COVID issues and things. Quite a lot to get through first before I introduce Antony. So welcome here. I hope you read the COVID information that was there. It's the IC COVID information. It's nothing unusual. For your safety and well-being, I've just got to issue some safety instructions with regard to as a meeting here tonight. Housekeeping. Please could I ask you to take a moment to check your mobile phones are off or that any other technical device is turned off as well. Could also remind you not to leave bags, personal items unattended at any time. In the event of a fire, the alarm will go off and we'll leave this meeting room by the emergency exits, which are at the back and here. The labels all the way through, and we'll go back out of the building at the front and we'll congregate round at Storey's Gate. So you go out of the building you've just come into, turn left, go along the road a few hundred yards, no, not even that, it's about 20 or 30 yards, and then left again into what's called Storey's Gate. There's a road at the side, and that's where the assembly point is. In the event of any other emergency, we'll be informed by a member of staff who will provide further instructions. So we stay here until we receive that. I'd like you to fill in the attendance sheet if you're prepared to do that. It's here. I've put a couple of wipes with it, and there's more wipes up at the front desk here if you need them, or sanitizer there. But it does help us actually track people, so we know who's actually been in the building. So I'll leave that. Sorry, I'll leave that down here. If you could, rather than normally recirculate it, I think it's probably better left here, and sanitizer there. If you would just fill it in, that would be grateful. That would be good. Right. Second November evening meeting, and I'm pleased that the IC have facilitated both the theatre here for the first time in about a year and a half for us, I think, is it? Sorry? Second. Oh, right. Oh, I missed the last one then, sorry. And also we've got members online as well. So it'll be a good meeting. If you've ever been in tall buildings and been uncomfortable in them, I used to work one in Collier's Wood in London, and in high winds, you get the vortex effect on the corner, and then the reattachment of the streamlines is a transient point, and so you get this oscillation. And whilst it was designed by a major consultant in the UK, it didn't have shear walls at the end. It had walls, but they weren't shear walls. They weren't stiff enough. So the whole building used to move like that. You've probably been in theatres. There's some London theatres where you can hear the underground travelling past while you're watching the show, which isn't very good. Or just footfall if you've been in buildings that are not very well designed in terms of the dynamics of the floor, and when you're trying to work and somebody's actually walking past you and you're moving around, not very comfortable. So we've all experienced this, and we've got rudimentary rules, design rules, which don't work. There's loads of buildings around that don't work. So I think we're all familiar with that. So tonight we're going to sort of look to the next stage moving forwards on that. And basically, what we need to do is understand the whole environment that we're dealing with. And three people I know: Alex Pavich, who you may have known, performing from Sheffield, now at Exeter. You've got Antony at Bath, and James, who can't join us tonight, unfortunately, the other speaker. He's also at Exeter, and they have actually been on top of this subject for decades. We used to have meetings. They used to come and talk to us about every 3 years. I used to invite them to tell us what they were doing. We're now in a position where we've actually got some really good kit around to really explore this subject, and that's what tonight's about. It's not a very catchy title, VSimulators. We did actually try, we had a competition to try and rename ourselves. We succeeded, we got a new logo. VSimulators, it didn't work, we didn't get a better title. So it's vibration simulation is the phrase we're looking at. And whilst we can't build loads of tall buildings and things like that and experiment with them all, it's a mixture of actual reality and virtual reality, and mixing those two, that's what Exeter and Bath have been looking into. So for me, it's the cross-discipline nature. We've got people in VSimulators who are actually, there's medical people who understand the physiology and psychology of people. So we're really bringing all those disciplines together. That's what's rather exciting. So to our speakers, as I say, James couldn't join us tonight, he's unable to make it. Bear with us a little bit, because Antony and myself, we're all familiar with all this, but Antony hasn't. It was probably today, I think, you finally got the presentation, so we may have a few hiccups as we go. There's quite a lot of videos and stuff in it. We'll see how we go. Right. Professor James Brownjohn is a Fellow of the Institution of Mechanical Engineers, Fellow of the Institution of Structural Engineers, and one of the leaders in vibration engineering section at the College of Engineering, Mathematics and Physical Sciences at the University of Exeter. His academic career has focused on experimental assessment of the performance of a wide range of civil engineering structures using full-scale dynamic testing, long-term monitoring, and physical motion simulation. He is a director of Full Scale Dynamics Limited, a university spin-off company that specializes in managing performance of civil structures dynamically excited by the actions of machinery, humans, and wind. He's principal investigator at the new Exeter VSimulators facility, which will study human experience with moving structures in virtual reality. Dr. Antony Darby is a chartered structural engineer and reader in structural engineering in the Department of Architectural and Civil Engineering at the University of Bath. His research expertise lies in dynamic testing, active and passive control of structures, and more recently, human perception and acceptability of dynamic motion. Prior to coming to Bath 20 years ago, he was instrumental in pioneering the real-time dynamic structural testing at the University of Oxford. He is principal investigator for the new Bath VSimulators facility, developed to allow multidisciplinary research into human experience to tall building sway, incorporating environmental influences and virtual reality. So, as I say, bear with it a little bit, and bear in mind we've got online guests, so I will take some questions from them later on. And Antony, I'll turn to you now, and thank you very much for coming up today. I really appreciate it.
Thank you very much for your kind introduction. Good to see a few people here, and good to see some people online. Give me a wave if you're online. I can't see you, but hopefully you're waving. So I'm going to start off with a few sort of rhetorical questions. First of all, why do we have buildings? We have buildings for people to work in, to live in, to do leisure activities in. Why do we design buildings sustainably? So sustainable building design involves us either avoiding or reducing the depletion of critical resources, so energy, land, raw materials, and so on. So there's sort of dichotomy there in that the reason we design sustainable buildings has nothing to do with why we have buildings. There's no mention of people there. So how do we currently design buildings sustainably? Well, we either use reduced use of conventional materials, so trying to design buildings optimally, reducing the amount of concrete and steel that we have in buildings, or we use renewable, sustainable materials, which really comes down to being sort of timber type materials. And that timber materials are inherently less stiff than sort of steel and concrete that we tend to use more of. So the combination of us having these sort of optimized structures where we're removing material, using the minimum material that we need for strength, and using materials that are inherently less stiff means that structural design is increasingly governed by serviceability considerations rather than ultimate load considerations. So although structural design is more governed by sustainability, so things like deflections and, more importantly in this context, vibrations, we don't really know what is an acceptable level of vibration. It really depends. As much as standards and guidance writers would like you to believe, there's no sort of one value for what is an acceptable level of vibration. It depends on all sorts of things. It depends on the context, it depends on what you're doing. So someone in a dance studio is going to accept a very different level of vibration to someone, a doctor in a surgery. So it's context dependent, and that includes, you know, the activities that you do, the surroundings, and all sorts of other environmental effects. So that is what VSimulators has been designed to look at, come up with rational design guidance for vibrations and motion in buildings and structures. So it consists really of two bits of equipment, one bit which is housed at Bath and one bit which is housed at Exeter. And combined, they cover the full range of vibrations and are able to simulate that full range of vibrations that structures and buildings are subject to. And by combining that vibration and motion with aspects of the internal environment, the influence of surroundings that we use virtual reality to simulate, and testing people's psychological and physiological response to those different stimuli, that allows us to see how all these things link together and allow us to work out how people actually respond to that motion and vibration, and allow us to assess the acceptability of that vibration. So I'm going to start off talking about the Bath VSimulator, which is a low frequency, long stroke biaxial motion simulator. So it's a big box on top of it sort of floats on top of these hydrostatic bearings, and is pushed by big actuators to produce this sort of large amplitude, low frequency vibration. And then that's coupled with environmental chamber that allows us to control the internal environment and virtual reality. So, and it's really designed to simulate sort of this sort of large frequency, low frequency, large amplitude motion that you will feel in tall buildings. I came across this in the Guardian. Wasteful, damaging and outmoded is it time to stop building skyscrapers. So the reason behind that statement was that to ensure that we have sufficient stiffness in our structures to prevent those large amplitude vibrations, you end up with about double the carbon footprint compared to a 10-story building of the same floor area when we start going up higher. So is it sustainable? Okay, well that's a good argument, and that's why we need to look at what are acceptable levels of vibration, because we're designing these things to certain standards, but is it fine or isn't it fine? So why do we continue to build tall buildings? Well, I found these two quotes from Arup Associates. So first one, 70% of the world's population are going to be living in urban areas by 2050. So basically we've got very little space to put all these people in, and so we're going to have to build upwards. So tall buildings, as long as we can engineer them well and safely and smartly, then we can help with that influx of people. And then this other quote is saying that wood can play a big part in building sustainable high-rise cities of the future, because it is a truly renewable material. And we're starting to see these sort of tall timber buildings. So the building on the right there is the world's tallest timber building, 18 stories, 85 meters high, made of CLT. Slightly perversely, it has the top 5 stories of that have concrete floors, and that was introduced because of the dynamic response of that structure. So it's trying to increase the inertial mass of that structure so it's not as prone to swaying in the wind. But regardless of that, it sways about sort of 140 millimeters in strong winds. And I'll come back to that building a bit later on. And there's all sorts of plans for even taller buildings than that using timber. So So I'm not necessarily talking about these sort of super tall, mega tall skyscrapers that we see, even sort of fairly modest buildings, sort of 14 stories and up would be considered a tall building and suffer from these problems of sway and vibration. So I'm just going to talk a little bit about the history of motion simulators. And the modern era of tall building design really started in 1972 with the World Trade Centers. Up to that point, the sort of skyscrapers that existed were pretty massive, very heavy, pretty stiff. So the Empire State Building, which famously was the tallest building in the world for decades, it sways about 200 millimeters from side to side in 100 mile an hour winds. World Trade Center, they were worried about this. This was much taller and a lot less stiff in terms of a building design, much more lightweight structure to go that tall. And so they were one of the first building designers to do wind tunnel testing on tall buildings. So they put in this wind tunnel, subjected it to 150 mile an hour winds, and the models moved by about 25 millimeters, which scaled up, translated to about 12 meters of sway at the top of that building. So they realized that this was going to be completely unacceptable, but what they didn't know was what is acceptable, what is an acceptable level of vibration. So they built the world's first motion simulator specifically to look at sway in tall buildings. They actually built two of them. This is the second of them. It's very sort of not great image, but it was basically a box hanging from cables. I think it was about 50 feet long cables inside a ventilation shaft in a tunnel. And it was guided by sort of bicycle wheels on the wall of this shaft. And basically some big hefty people pushed it from the outside and swung it from side to side. There were people inside who didn't necessarily know they were being tested for vibration. And say that this was one of the sort of first tests to try and ascertain whether, you know, people would sort of suddenly realize something wasn't quite right. So they got them to do these sort of eye tests and things like that. So that's what they thought they were doing. And then eventually they realized that something wasn't right with this room. And this sort of pioneering work demonstrated a few things that are sort of commonly known today. That first of all, the period of vibration affects how you perceive, or the level at which you perceive that motion, regardless of the acceleration. It changed that acceleration where you perceive the vibration changes with that frequency or period. Whether you're standing up or sitting down makes a big difference to how you perceive the vibration, and whether you have knowledge of the vibration before that you're in a building that's going to vibrate before affects your perception levels. So the perception levels were much higher when they didn't know this building was going to vibrate to afterwards, when they're told that they were going to move and they were ready to, you know, to see to measure their sort of threshold. And eventually, you know, they fixed the problem with the vibration of the World Trade Centers by putting in 10,000 dampers. So they had these little viscoelastic dampers that they put in each floor, 100 per floor, and that reduced the accelerations that people would feel to about 16 milli-G. So it's 0.016 of the acceleration due to gravity, which is still pretty high, but that's extremely high wind loads. And so since that work, there's been a lot more work. Now, ideally, we'd want to be testing people in buildings, but getting access to buildings, and there's plenty of buildings that have sway problems. But getting access to them and the people in them is incredibly difficult, as you can imagine. So motion simulators are a good way of simulating that motion in a controlled way and testing people. So this has been sort of going on since the 1980s with these motion simulators, more complex motion simulators. And this has led to various vibration serviceability criteria. So there's loads of different stuff, but it all sort of goes back to this very early work on perception thresholds. So pretty much all of this work, all of the design serviceability criteria are based on perception thresholds. They're not really based on whether that motion is acceptable or not. And there's a lot of sort of conflicting information out there that makes it difficult to work out what is the sort of definitive criteria. And say the point is there's probably no definitive criteria. It will depend. So what is wrong with current guidance then? Well, first of all, it is based on these perception thresholds, which are based on either unidirectional sinusoidal motion or elliptical or circular sinusoidal motion, okay, which is really handy for defining perception thresholds, but it doesn't resemble the sorts of motion that you feel in practice. So you need to consider the fact that you have different natural frequencies in different directions in your building. The wind is not constant loading, okay, so it doesn't produce this constant sinusoidal motion, even if that was what the building wanted to do. So when you actually measure the actual response of buildings, it's very far from being sinusoidal in nature. So that's some actual measured displacement motion from a building in Japan. And so you can see there's neither elliptical nor sinusoidal. So it really doesn't represent the type of motion that you're feeling in a building. Secondly, what is the best measure of motion? So some guidance documents say peak, some say RMS, root mean squared motion. So is it right that we should be using a peak motion, peak acceleration that you feel very infrequently, or should we be using root mean squared motion? Well, if we look at this, sorry, it's a very blurry picture, but all of those motions have the same RMS value, but the quality of that motion is completely different. So again, it doesn't really tell you anything about the sort of motion that you're feeling. And then things like exposure, habituation, and there's something called sopite syndrome, which was discovered by NASA scientists, that sustained exposure to this sort of gentle swaying motion causes the sort of onset of motion sickness type and tiredness and lethargy type symptoms. So it's the same sort of motion that we use to rock children to sleep. So it's sort of inbuilt with us to sort of feel tired and lethargic when we have this low frequency motion. And that might be fine at home if you're feeling tired, but it's probably less fine if you're at work. And then context dependency. So there's the ISO 10137, which is probably the standard that most people refer to when looking at tall buildings, has a sort of nods to this context dependency by having two different levels of vibration acceptability for residences and offices. So in this graph, frequency, you've got frequency along the bottom axis there, and you've got acceleration, peak acceleration, acceptable levels along the y-axis. So it's suggesting that at residences, you should have a lower acceptance criteria than for offices. And the only reason for that is that someone's thought to themselves, well, we spend 2/3 of our time at home, 1/3 of our time in the office, so we ought to have a more stringent criteria at home because we spend more time there. That makes no sense whatsoever. We do completely different things in those two environments. In an office space, it's fairly sedentary and we're having to concentrate on particular work tasks. Whereas at home, we're doing all sorts of different things. Half the time we're asleep, half the time we're sort of cooking or watching television or whatever we might be doing. So it doesn't really capture that context dependency in a meaningful way. And then all this motion simulator work has been done looking at deliberately just looking at the motion itself without looking at other cues to indicate vibration. So buildings do creak when they sway. Using perception thresholds as a proxy for acceptability in building just doesn't make any sense. So James Brownjohn always hates it when I use this analogy, but I'm going to use it anyway. I think it holds up. So if you consider train travel, we expect there to be vibrations and motion. We expect to be rocked from side to side, accelerating and decelerating. Does that mean that it's not acceptable just because we can perceive it? Well, of course not. But it may cause us to go to sleep, and that might be fine. A lot of people fall asleep on the train. It might be fine in the morning or leaving work, but it might not be fine, again, if you're trying to work on the train. And no one's going to say that there's not discomfort on a train. No one's going to say that it's not going to affect your ability to work on a train. So those are the things that we need to be looking at when we're talking about acceptability of vibrations, whether that's, in a tall building or any other type of vibration. So this is what the Bath VSimulators has been designed to simulate. So it's this large amplitude vibration. So this is from our factory acceptance testing. This is the actual platform. So that's showing the sort of extent of the motions that we can simulate. And this is showing that this is doing some sort of elliptical motion. As I say, that's not necessarily typical of what actual motion is in a building, but it can simulate any sort of, it can replicate the sort of motion that you do feel in a building. So the red there is the desired response from a measured building response, and the blue is what we're simulating there. And so if we zoom in there, we can see that we can match that pretty well. We can pick up the sort of higher frequency components of that vibration and be able to replicate that pretty well. This is the performance envelope. So we've got acceleration on the vertical axis, frequency on the horizontal axis. And so what we're looking at are these very large amplitudes. So we can move plus or minus 400 millimeters. We can go down to about 0.05 hertz. So below what, that'd be a sort of super tall building frequency, natural frequency. So tall buildings are typically around sort of 0.1 hertz. Natural frequencies, and we can go down to these very low accelerations of 3 milli-G that we can simulate, or perhaps even lower than that. So that's the area that we can sort of simulate, the region we can simulate. And then on top of this motion platform, we have this climate chamber, and that allows us to simulate things like light and sound. We can change light intensity, like color, temperature. We can change the fresh air intake that we have. We can change the air temperature. We can change the humidity. So all of these other aspects that influence our comfort and health within a building. And then added to that, we've got this projected virtual reality in the case of the Bath VSimulator. So that allows people to do sort of work activities and things and still have a feeling of being in a larger space. So we have an open plan office building, a modern apartment building, so we can simulate those sort of two different types of scenarios. We can change the view outside, so a low-rise city or a high-rise city. We can change the time of day from night today, and we can change the height that we are in the building as well. So all of these things that influence your perception of vibration, and more importantly, the acceptability of that vibration. So we've been, and then on, alongside that, as said, we can measure the physiological and psychological response of people. So we wire people up to all sorts of physiological measurement things and get them to do sort of work tasks and see how they perform in those work tasks. So our current tool building motion research that we've been doing, this sort of fairly recently, has been looking at how people do respond to these motions. So we subjected people to high acceleration motion, to medium acceleration motion, and to low acceleration motion at 2 different frequencies, 2 natural frequency buildings, one which was 0.2 and one which was 0.5 hertz. So we started off with the highest acceleration being 12 milli-G. That was a peak acceleration, and people were feeling sick. So we had to reduce it a bit. So we moved it down to 10 milli-G, and we didn't have any more complaints about people feeling sick. But that tells you something about the sorts of level of motion that's already there, sort of not necessarily acceptable to a lot of people. And we also had a control test where we didn't subject them to any motion, and we just did this in a random order, so they didn't know what motions they were experiencing. And it wasn't just sinusoidal motion. We were putting in this sort of simulating real building motion and it was in two degrees of freedom. It wasn't just in 1 degree of freedom as well. So this is sort of fairly typical. So this is for a 6.5 milli-G peak acceleration with a peak factor. So that's the ratio of the peak response to the RMS response of 3.5, which is fairly typical for building motion. And it sort of repeats itself every sort of couple of minutes. And this shows those acceleration points on our acceleration frequency graph in comparison with those so-called comfort criteria from ISO 10137. So you can see that most of those are below the criteria for offices, and some of them are below the ones that they've defined for residential buildings there. So those are the yellow dots for the actual acceleration, peak accelerations that we expose people to. And then we got them, say, to do various psychological tasks, which measured various cognitive abilities. And at the end of those tasks, we produced what we call a productivity score. So that's the reaction time, basically how quickly you do these tasks compared to the accuracy, divided by the accuracy. So a higher score indicates lower productivity. Okay, higher productivity score, it means a lower productivity. And so these are the results. So let me just explain what these graphs are. So on the vertical axes, that's your productivity score. And along the x-axis for each of these, that is the frequency. So we have 0 frequency, so no motion on the far left, and then 0.2 hertz and then 0.5 hertz. And so each of those graphs, the one on the left is high accelerations, one in the middle, medium acceleration, these are peak accelerations, and the one on the right are the low accelerations. And so you can see that there's a deterioration regardless of whether you got high or low accelerations as those when you have motion. Okay, and as I say, people weren't prompted to whether or not there was motion going on, and some of these were below the perception threshold that people would actually perceive. And as you would imagine, for the higher accelerations, the productivity was worse than with low accelerations. But regardless, even though you couldn't necessarily perceive those vibrations, there was a deterioration in your productivity. And then we did these sort of longer term tests. So those sort of was quite short-term tests. These were sort of longer-term tests where we exposed people for 2 or 3 hours to sub-perception threshold motion. So people couldn't feel this motion, and I experienced it myself. I couldn't tell when we were moving and when we weren't moving. And half the people were subject to no motion, and half of them were subject to motion. And again, we tried to see over time whether there'd be a deterioration in your performance for these work tasks. And again, we sort of showed that when there was no motion, there was hardly any deterioration or hardly any change in your performance. But with the low motion at the end of the test, your performance for these work tasks was worse than at the beginning. Okay, so that sort of indicates that this sort of sopite syndrome thing exists. And then we also gave them a questionnaire where they had to talk about their work performance and how they perceive their work performance having changed. And so this is the other way up, and just to confuse you. So a lower score here indicates that they perceive their work performance as dropping off. Okay, whereas previously a higher score was indicated lower work performance. So you can see again, just from people's own sort of perception of how they performed for a particular task for these different acceleration levels, people thought that their work performance was also getting worse. And it almost mirrors exactly what I showed previously. So those are the previous ones from the actual objective measurements from their performance in these tasks and their subjective evaluation of their performance. And then we also asked them about their comfort level, their perceived comfort level. And again, you can see that, regardless of whether you could perceive the motion or not, even at these very low level motions, they thought that they were less comfortable. They perceived it as less comfort. And obviously, as those accelerations got higher, people were even more and more uncomfortable. So that's that's the sort of current research, and that's something we're sort of looking at in more depth in these tall buildings, because we know now that these criteria, even if you meet the current criteria, doesn't necessarily mean that your building is okay. Okay, now I'm going to talk about the Exeter facility. So the Exeter facility is looking at a different range of vibrations. Okay, so James Brownjohn gave me this presentation, so I'm going to try and make sense of and what he's trying to say in his slides. So forgive me, James, if you're watching. Forgive me if I don't put this across quite how you wanted it to. But I'll try and guide you through this. So the Exeter Exeter VSimulator is a 6 degree of freedom simulator, whereas the Bath one only moves laterally in 2 degrees of freedom. This can move up and down, it can move side to side, and it can rotate and yaw, pitch and yaw. So 6 degrees of freedom, but much smaller vibrations. So I think it can move up to about 25 millimeters, plus or minus 25 millimeters as a maximum acceleration. But importantly, it can go down to micron level vibration levels, so down to 5 microns or possibly even less than that. Accelerations up to about 2 meters per second squared. So those are very high acceleration levels. And it is a 3.6 meter plate, very lightweight, but very stiff plate. This is on these electrically driven actuators. And that whole plate is a force plate. So you can measure the actual force that people are applying to to the structure as they're interacting with the structure. And so just want to talk a little bit about the sort of drivers for the simulator. So, and this applies to both simulators. So we know, as I said already, serviceability is increasingly governing design, and we got a whole load of quotes, and we talked to a whole load of people in the industry to reach that sort of conclusion. So these are just some of the quotes. So human perception of vibration is increasingly governing design. Serviceability and human comfort has become governing. Vibration serviceability is a design driver. Acceleration, response, and habitability performance of tall buildings can cost firms millions. Embodied energy is then driven by these vibration effects. So it's clearly a really important driver for everything that we're doing with these simulators. Coming back to this tall building, so say with medium high-rise buildings, the Exeter facility can simulate some of these shorter tall buildings, for want of a better description. But we know that design codes are contradictory and not necessarily appropriate. It doesn't give you an appropriate level of vibration. And it's really the end users that we need to be looking to. And if we end up with these buildings that don't meet the criteria, that are unacceptable, then it's going to be very expensive and very unsustainable to try and fix, and we might not even be able to fix them satisfactorily. And I say that current vibration guidance just doesn't consider all the other environmental effects. So these are two buildings that Exeter have been looking at, and they've been shaking those buildings and working out how they respond. Both of those are sort of fairly flexible buildings, and and they're timber buildings, and and they are particularly prone to sort of vibrations. And so those are sort of things that we want to be looking at. And then, of course, things like lightweight footbridges. We all know that they are particularly susceptible to human-induced vibrations. So understanding both vertical and sway vibrations of buildings and trying to sort those out, sorry, not buildings, but bridges, and trying to sort those out is another key driver, particularly for that Exeter VSimulator, which can simulate all of those different types of motion. Another one, this is a football stadium, people jumping, people dancing at concerts. They move a lot, and the Millennium Stadium is a good example of something that had to be retrofitted to prevent excessive vibrations in those sorts of circumstances. So they put in these additional props when they've got sort of concerts going on. And again, one of the virtual reality scenarios that Exeter have is a big stadium. And so that's something that they also want to be looking at. Floors. Okay, and this is a big thing. Lively floors in buildings. And I think this is one of the main drivers for the Exeter VSimulators is understanding how floors respond to vibrations and coming up with solutions to prevent that vibration. So they've done a lot of work on these active mass dampers, very low profile active mass dampers that they can put in floors and prevent vibrations. But there's been numerous floors that Exeter have looked at which are problematic, particularly in things like hospitals. And this has all sort of been picked up in the design for zero. So I don't know if you've come across this. It's been recently published online and in paper copy as well. So Doesn't seem a very sustainable thing to do. Never mind. So the iStruct have published this guidance, Design for Zero, thinking about how we can get to our targets for net zero buildings. And as part of that, they recognise that we need to, that as we build these sort of optimized, lighter buildings, using less material, using less stiff material, that serviceability requirements are going to sort of govern their design. And they recognise that serviceability criteria aren't necessarily appropriate, and our sway limits really fit for purpose in terms of well-being, comfort, productivity of occupants. So we need this evidence-based design for these future buildings. Okay, so this is talking about walking data, so how people actually interact with these sort of lively floors and lively bridges, and we've got very good data, except very good data on how the sort of forcing that people apply to structures, and that allows them to model those structures and replicate the motion of those structures using VSimulator. And thinking about these sort of assessment criteria, we understand very well how to model the source of vibration. We understand how to measure the response of the structure to that source of vibration, but the receiver, us, that's the bit that we don't understand. And so that's the missing link there that we're trying to fill with these simulators. And so we're in the situation now that floors that are designed to the current specification actually in reality are not serviceable. So what is wrong with that specification? And it's complicated by the fact, as we said, that there's different acceptance criteria. So this is looking at response factors. So the graph on the left there is the sort of base acceleration, acceptable acceleration curve, again, according to ISO 10137 at least. And then you multiply that by a response factor depending on what you're doing in this building, whether it's residential, office, or whatever it is, and how long you're spending in that building. So these are two different guidance documents that have completely different response factors for the same thing. One is 4 and one is a response factor of 8. So which are you going to choose? Well, you going to choose the one that is easier to meet, the response factor of 8. But if you use that, is that going to be acceptable in the real world? Well, quite possibly not. And then this is the wood building again. So this is the monitoring that's been done on these buildings. And we're sort of seeing that the vibrations under sort of typical wind loading, actually fairly small, but you can still feel it, or you can feel that something's not right in the building. Yet we're designing to these very rare occurrences, so once in 5 years, once in 5 year return periods for wind loading, which might be 18 milli-G might be acceptable, but those happen very rarely. These things happen every day, and people are still feeling them. So should we be using these very rare events, or should we be using the typical daily events to design our buildings? So what is that sort of return period that we should be using? And then, so again, this is a school. So this is part of some work's that's been done on a floor in a school. So they went to school, they did a 360 video of the school, so they can then simulate in 3D what it's actually like in that classroom, and measured the response of the floor to people walking around this floor. And then you can replay that on the on the Exeter V simulator, have the 360 video. I don't think that was actually implemented, but we can do that now. So you can feel like you're in the space, feel the vibrations in the space, and then do sort of proper controlled studies of how it feels to be in that environment, and again, what that is an acceptable level of vibration. Okay, and then this is looking at a wobbly footbridge. So this is some work that's been going on at Exeter on fibre reinforced polymer footbridges. This is a very lively footbridge, as you can see. We measure response as you're walking along it, and then we can simulate that again using so you can simulate exactly what it's like walking along this bridge on the simulator. And again, you've got a more sort of controlled environment to do sort of proper studies of what's acceptable or not. And you can replicate almost any sort of vibration like that. So I know that James has measurements from buses, boats, and trains as well, so you can simulate the vibrations that you feel in those environments. And then one big thing that Exeter started to look at is applying it to sort of health situations. So that was a little video. I'll play it again, and if you just look, I'll have to go back and okay, just look at that bottom left. Oh, actually, you didn't see it. It just sort of hung as it other way, but it just did a little perturbation sideways, only a very small amount, and it was looking at how you can lose balance. So, and those sorts of things become really important, particularly for aging populations and people with movement disorders. So there's a lot of health research going on and mobility research that can be explored using the simulator. And this was a little bit of research looking at evaluating the capability of portable shakers to test buildings. So to get a building to start moving, one thing you can do is get a great big shaker, big mass, and move that mass and get the structure moving, or you can get a whole load of people in the building to move at the same time at the natural frequency of the building, and you can get the building moving quite a lot by doing that if it's a flexible enough building. And then lastly, looking at sort of commercial applications. So both for the Bath V simulators, tall building simulator, and the Exeter V simulator, we're very keen for to explore commercial applications. So using the V simulators for people to actually, clients and designers to actually experience these vibrations. So if I say, 5 milli-G, what does actually 5 milli-G feel like? I guess most people don't actually know what it feels like. So to gain them to experience that and gain them to think about that variation in duration of exposure to those different natural frequencies, to allow you to come up with design decisions and design criteria for your building. So if you're interested at all in in working with us and hiring the facilities, then obviously you can let us know, come to our website, and we can talk to you about that. Just one last thing, talking about the calm floor system, which is this sort of active damping system that can help with floors and so on. Okay, so just to sort of summarize then, sustainable construction practices need to consider the users of buildings. It's not good enough to just think about sustainability in isolation to meet these sort of sustainability criteria without thinking about the effect that that has on people, whether that's building vibration or whether that's to do with the internal environment or whatever. It needs to focus on people's comfort, well-being and work performance, not perception thresholds. Okay, they're completely different things, and acceptability depends on that comfort, well-being and performance, not on perception. The VSimulators facilities have been specifically designed to explore these aspects and how these vibrations and environmental effects affect people, and that hopefully is going to lead to this context-dependent design criteria and help inform that sustainable development for the future. We can help with designers and clients to experience those vibrations and help them come up with economically viable solutions to meet those acceptable vibration characteristics. And as I say, there's all sorts of other applications outside of the world of structures that we can use these VSimulators for in health and transport and so on. So please have a look at our website. There's all sorts of information about the VSimulator on there. I do need to thank James in particular for preparing those last few slides. His colleague at Exeter, Alex Pavic, he's been very much involved in the VSimulators. My colleague who used to be at Bath, now at Surrey, Ian Walker, who is Professor of Psychology, and my PhD student, one of my PhD students, Kaveh Heshmati, who was doing the research that I presented for the Bath VSimulator. Okay, so that's all I want to say. But if you've got any questions at all, I would be very happy to answer them.
Thank you very much indeed. That was really good, Anthony. Thank you. Right, we have a lot of people online and a few people in the room, so I'm taking any questions. I've got a couple online, but any immediate questions? Yes. In fact, could you help take that around the room? If you're worried about using the microphone, just keep it away from you, but there are sanitizer sachets here as well, perhaps. You might take those around as well. Is that all right? And if you're concerned, you're welcome to come and sit here and just use one of these standing up microphones if you're worried. Okay. So any questions? Starula.
Thank you very much. Really fascinating presentation. Amazing project and work. I had my name is Sarula Konto. I'm from Imperial College. I was very interested in the trend that this tolerance criteria have with respect to frequency. When I have done work involving and B, whether you think you're going to be confirming that trend in terms of frequency with your experiments.
Yeah, that's very good question. I think we're already starting to see that trend. I mean, for the stuff that I've been doing, that's that lower bit, so the bit where it starts to go up again in the very low frequency range, and yeah, we're definitely seeing that trend, but it literally just comes from tests and And I think that is one of the things that we want to get to the bottom of, is trying to understand the physiology behind how people are perceiving those vibrations, because then that helps us inform how people measure the acceptability of that vibration. So certainly with those very low level vibrations, it tends to be the vestibular system that is your main source of feeling the vibration. But yeah, I don't know why there's that sort of increase as you get lower and lower frequency. So it's an interesting point, and it's borne out by previous research, borne out by our current research, but the reasoning behind it, I'm not totally sure why that is, but hopefully we'll be able to answer that in the future.
Sure, thank you.
Oh, and interestingly, I'd just say that some of the other design criteria around the world, it completely ignores that frequency dependency. They just have a set threshold, and that is it. So in the US, for example, or in Canada, they just have a set threshold, and which is independent of frequency.
Okay, any more here? Otherwise, I'll go online. Okay, probably just a fairly fundamental one that you can answer. The bath facility. Somebody's asked, Khalil Zayed has asked, can you control the pressure inside the chamber? Now, that's not something I'd actually thought about.
Yeah, no, we can't. It's not completely sealed.
Yeah.
So yeah, we can change the pressure in the chamber.
Interesting, though.
It is. Yeah. No. And it probably does have some effect. Yeah. But, yeah. There's probably some application that that person's got in mind, but yeah, no. Sadly, we can't do that.
There's Peter Rangelo, Basler Hoffman, Argate, that's Germany, I think. The condo board at one of New York's tallest and stoniest towers sued the building's developers, claiming design flaws are to blame for flooding, stuck elevations, and, quote, horrible and obtrusive noise and vibration. So I think that's just really supporting the work you do.
And it's definitely not the only one as well. And the trouble is, some of these don't meet the current design criteria. Some of them do meet them, yet they're still problematic to people in those buildings.
Yeah. I mean, to me, it just shows the value of the facilities you've now got.
Yeah, it's a common issue.
Yeah. I was also interested, is it British Maritime are very interested in doing some work, because they've got the ship motion that they're interested in, aren't they, which is very low frequency.
Yeah, and using the virtual reality as well allows us to simulate all sorts of different applications like that. But yeah, sort of, it's very similar to sort of ship motion, but you also got the sort of pitching there as well. So yeah.
Andy.
Andy Jackson from Atkins. I'm just wondering, in terms of the existing codes, you've sort of established that they're not quite fit for purpose. What is kind of your aim with this research? Is it to establish a code which is a little bit kind of more representative of kind of the realistic reception for humans in buildings, or are we looking at bespoke building design for everything?
Okay. No, that's a very good question, and I mean, I think we would like to produce some better guidance or a better code that sort of truly represents the acceptability. But as I say, that's very context dependent. So I think there needs to be it needs to be sort of more refined than it is now, and as I say, definitely not based on perception thresholds, but also thinking about what is the best measurement for that acceptability, and it probably isn't RMS, it probably isn't peak values, might be jerk is a good measure of how people respond to motion. Jerk is the time derivative of acceleration. Acceleration is nice and easy to measure, which is why people use it. But jerk is actually how we feel vibrations. But also things like vibration dose values, which has a sort of time dependency associated with it. And that's used in other aspects of vibration, but it's not used in building vibration. So there's lots of things. So yeah, there's lots of aspects to it. And I don't think we're going to, I think we're going to get something better than there is now in the short term. But in the longer term, I think there's still going to be a lot more to explore. And I think you're probably right there. It ends up being more bespoke design guidance for particular building, for a particular application, particular location, and all those sorts of things, rather than a one-size-fits-all type design guidance.
There's a gentleman at the back, I think. Was that all right? And then we'll go to you. That's all right. Yep.
Actually, Andy, really sorry. My name is Alan from Artikins as well. Andy just asked this question I wanted to ask.
Okay, all right.
Done. I won't give the same answer again.
But just to build up on that, so I do quite a bit of blast assessment, and there's a lot of power, I think, to the clients really to come up with acceptable performance criteria. So you typically find in blast design that you find that the client actually comes up with the perceived level of damage that they want on their structure. So I'm just curious, having in a commercial level, how much power does the client have? And secondly, in the test that you've actually done, I'm very curious, have you undertaken a test where you kind of induce placebo to the testees and say, look, we're not inducing any motion in this, but you tweak the value, and how does that affect the results that we actually see?
Yeah, so your first question, clients, I mean, that's the clients, I think the clients, when they're sort of dealing with sort of blast loading and things like that, are probably better informed than the clients who want a tall building. And I suspect, and I don't know, I mean, you probably need to tell me, the clients are probably going to want to take a steer from the designers rather than, but the client ultimately is the one who has to sign off whatever design criteria they're happy with. And I guess that is, somewhere where, getting the clients to experience those levels of vibration in a simulator, one of the simulators like we have, is quite valuable. It doesn't tell you everything because it is a simulator that you may be there for a few hours. It doesn't tell you what it's like being in the building for a year, but it will give you at least some sense of what a reasonable level of vibration might be. So yeah, I don't know the sort of dynamics, for want of a better word, between the client and the designer and the developer and so on. But yeah, someone's got to actually agree to something, but it requires some sort of steer from someone. To answer your second question, zero motion, yeah, so everybody that we tested, we said we did it under multiple acceleration levels, and there was at least one where there was zero motion. So they didn't know what order we were doing these in. They didn't know whether they were moving or not. Sometimes it was obvious at the higher accelerations, sometimes it wasn't. And we certainly got, anecdotally, some people, so when we did the sort of longer term tests where people were in there sort of 3 hours, half of them, say, were subject to no motion, half of them were subject to this below threshold, below section threshold motion, and there were quite a few who came out with the no motion saying, oh, I kept feeling vibrations. And that's the thing, if you know you're in a test where you're going to be subject, possibly going to be subject to vibrations, you're sort of thinking, am I moving or aren't I? I was thinking that when I'd been in there as well. Has it started moving yet? I don't know. So it's important that you do have those sort of placebo ones, those control ones in there, because people are sort of on high alert for any sort of motion.
Did you want to have, Andreas? So I've got one from online. So.
Okay. Yes. Hello, Andreas Nelson Atkins. Thank you for a very interesting presentation. So I wanted to ask, assuming you now succeed in deriving these new criteria for acceptability of vibrations, presumably to design and build new buildings, we will need to analyze them. We need to predict the level of vibration through analysis, in particular numerical analysis. How good are we at that at the moment, is your feeling, is your understanding?
I think actually pretty good. So there's a lot of sort of post-occupancy measurements of vibrations in tall buildings, which designers have, and clients allow them to collect, so that they can sort of look at it, but they never release this at all to the public. So it's really hard to get hold of, but it exists. So and so that gives designers confidence in that what they're designing to actually is actually represented in reality. So I think, you know, with the sort of computer technology and the wind tunnel testing and all those sorts of things, really good at modeling the structure, really good at modeling the source of the vibration, whether that's wind loading or whether that's people pacing up and down or whatever it might be. But yeah, the last bit is the bit that we're not very good at, is saying whether or not it's acceptable. But having said that, yeah, there's still situations where it's not right, and things like damping is the level of damping in your building. You just sort of have to take an educated guess on that. You don't know what it is until you've built it, because there's so many sources of damping. And that has a huge influence on the actual response of your structure. So there are things that, you know, I guess people aren't as good at, but, you know, probably, you need to speak to the designers more. They'll be able to tell you whether they're confident about their models or not. But I think that's a perception that I get from designers that I've spoken to.
Thank you very much. I'll go for one online, if I may, Andreas. Yep. It's Paul Doyle of Jacobs UK, senior consultant. People on a ship are subject to vibration most of the time, and quite large motions at some time. On a cruise liner in a storm, it's quite notable that people move in sync on very strange paths. Has this been considered as another source of vibration tolerance? I think that's in hand, isn't it?
Well, yeah. I mean, the moving with the movement of the structure or ship or whatever it might be. Yeah, that's a natural response to the sort of lock-in that you have. But habituation, there has been a little bit of research done, and we're doing more with some sort of surveys of people in buildings. And what they found is about 40% of people say their tolerance of motion, it probably comes down to tolerance of motion rather than habituation to it. They tolerate the motion, their tolerance of the motion improves over time. That's about 40% say it gets better. They're not bothered by it as much. About 40% say it doesn't change. Okay, they're just as intolerant or tolerant of it than they were 3 years ago in their tall building, and about 20% of people say it gets worse. They feel worse having been exposed to it over a long length of time. So, and I think it's probably pretty much the same on ships. Some people just never get used to that motion. Some people fine. Some people do get used to it, and yeah, hopefully most of the time ships don't move around too much, but obviously, you know, most boats do, or all boats move constantly. So so there is no sort of set answer to that. There's different people experience habituation to motion in different ways.
Yeah, you've got quite a challenge, haven't you? I think it was at the end of your response to Andy's question, in terms of vibration dose. You know, you might go over the Millennium Footbridge, but you're only on it for a few minutes. But it's quite interesting. You stop and sort of want to try and feel what's happening. Yeah. And then you're gone. You're on your journey on solid ground. So I think that's a very difficult area, isn't it? The how long you can put up with something.
Yeah. No, exactly. And if it's a gale force storm outside, then you're going to expect, you know, higher motion in the building, and you probably accept that higher motion, even if it does sort of affect you in terms of your comfort and your ability to work. You'll be more accepting of it than, you know, if you're feeling vibration constantly all day long, even if it's very low level vibration. So, and that's the, you know, so there's a sort of an education part of it as well. You know, can we educate people to accept different levels of vibration? Because I guess the feeling of buildings is that they don't move. You know, you don't expect a building to move. You don't, and you know, whereas you expect a train or a boat to be moving constantly, you don't expect that of a building. But every building is moving. You know, this building is moving now, the floor's vibrating now. It might be too small for you to feel, but it's doing it. But there'll be some which are worse than others. So if you then say, well, okay, you're going to be working in this building, it does move back a bit, you will feel it every now and then. Your acceptance, your feeling of acceptance of that may change.
Absolutely. My boss, when I started out as a young engineer, so that's 40 years ago, he was staggered even then. That, I mean, he was a very good dynamic analysis. He was staggered even then. He said all engineers try to put everything in the static or pseudo-static arena, and they look at everything really statically in those days. And he said, but the whole world, as you just said, Anthony, the whole world is dynamic, and we try and present everything static for when we look at things. And that's moving on with all the work you're doing, and also the way the educating ourselves as well. I think from what you've just said, there's a phenomenal future to understand these variables, because the one changes, but it influences all the other, and then there's a feedback loop, isn't there? Will was just referring to.
And it's sort of quite daunting, because there's the scale of what we don't know is huge, and yet we're still building these buildings.
Absolutely.
So, but hopefully we can sort of make some improvements as time goes on.
Excellent. Okay, have we got any more questions here just before we start to wrap up? Okay.
James Benson, Atkins. One question was, how were you able to sync up motion in the virtual environments with the real world motion? You were talking about cues, factor into perception, like light swinging. Is that something that's been done, or something that can be done?
Okay, so I don't know whether Exeter have implemented that, but they've certainly been looking at it with their virtual reality, making sure that the virtual reality, so they're using headset virtual reality, does link directly to the motion. So if the structure is moving, then virtual reality will move in sync with that. We have that to a certain extent with the Bath VSimulator as well, which uses protected virtual reality. So the outside scene moves relative to the inside environment. So we can sync that up. Again, we haven't fully done that yet, but yeah, that is the next stage of the development of the simulator, because that's quite an important thing to be able to simulate, particularly when the vibrations are quite large. because it does affect you. Yeah.
Dean Benson, Core Consulting. Just a very quick one in terms of applicability to your systems. I think one thing that's going to come in the future is a change of use of buildings. So as we go from maybe in London at the moment, particularly with COVID in mind, you're going to end up with maybe changing those to domestic use. So I think there's an opportunity there, and I don't know whether you've looked at it in terms of looking at how you adapt those buildings. You've talked about new buildings, but adapting old buildings is going to be, I think, a significant use of this product, because you don't want to end up with a customer downstream who's bought his lovely flat at £1 million, and suddenly the thing is swaying and creating those problems. So that transition, is that something anybody's going to talk to you about?
Not explicitly, but I think that is a very good point. I mean, reuse and redevelopment of buildings rather than knocking down and building new things, that's a big hot thing at the moment. That's one of the ways that we are going to have a sustainable future. And yeah, given that there are different, as I've said, there's going to be different levels of acceptability for different activities, different building uses. That's a really good area to explore. Yeah, thanks.
Good, thank you very much. No more questions here? I haven't got any more online unless there's anybody last question. No? Okay. Well, thank you, Antony, for both delivering your own presentation and also James's. And James, if you're still online, I hope you get better. And thank you very much for the preparation of your presentation. It was excellent, thank you. So I'd like people online can just put a thumb up, but people here, if you could show your appreciation for Antony's service. I have a little bit of business just before we close. The next meeting, looking ahead, is on the 12th of December. It's a joint EFIT, SecEd and iStructE meeting. It'll be held online. This event showcases the findings of 2 research projects undertaken by the 2019 EFIT research grant winners. They are Optimal Design of Rubber Joints for Seismic Protection of Masonry Infield Frame by Enrico Tubaldi, and Integrating Earthquake Early Warnings into Organizational Resilience by Giancarlo Pissaroli, Carmen Glasso and Omar Velasquez Ortiz. Could I also just, as you leave here, suggest that as you look forward in your careers, if you spend more time looking at this is the future, as far as I can see, in our dynamic environment. Think about damping. Try and understand what damping is. It's got many different forms, but if you're putting motion into a cyclic oscillator, the degree of response is heavily governed by the damping. The damping is the only way of taking energy out of the system. So if you're pumping it in, it's got to go somewhere. It'll either excite the system or the damping will actually take that energy out. So you need to understand damping. I should add that we discussed ethics, didn't we, about all these people you're putting in the boxes. That was a difficult time, so are you damaging people by investigating this? So I think that's a very interesting area, and we did struggle with it for a while, didn't we? So that's important. And could I say, Antony, and I'm sure James will as well, do come back and talk to us again in a year or so when you've learned so much more.
Yeah, will do. Yeah.
So one last thank you. Thank you again. And the bar's closed here for people in the auditorium, but if you go out, go left and go left again, just down the road, there's Westminster Arms. I'm suggesting we might have a brief little drink there before some of us depart home. You've got to get back for your daughter's birthday today.
Yeah, apologies. It's my daughter's birthday today, so which I planned badly. I got told off. Yeah. So I need to leave.
So Antony will be departing straight away, I'm afraid, which is a shame because he'd be happy to answer questions otherwise.
I'd love to, yeah.
I'll see you around there for a drink if you can manage it. Okay, thank you very much. The meeting's closed. Thank you.